Okay, so you have this mode which has no dispersion. It has a constant frequency as a function of k. Now, if you're in free space, you know that electromagnetic waves or photons will have a linear dispersion relationship of frequency versus k, and this basically corresponds to virtual charge oscillations in vacuum. And if you think about what happens if you bring these together and you make them interact, which can happen in a nanoscale system like this or at the surface of a metal, you will have a standard avoided crossing that is present whenever you have interacting systems. So you have this linear dispersion relationship of the photon, and you have this constant dispersion of the bulk plasmon mode, and instead you will get now two modes which avoid that crossing point. So you will get a lower branch which looks like a photon down here and then curves to become more plasmon-like over here, right, which is this charge oscillation. And you have this other mode which is photon-like at high energies and becomes more plasmon-like close to the bulk plasmon energy, right? Now, what makes this really interesting is if you think about the characteristic electron density of metals, this surface plasmon frequency is in the visible to ultraviolet range, right? And for that, the corresponding wave vectors that you have for photons happen to correspond to wavelengths on the order of hundreds of nanometers, right? You know the visible range is 400 to 700 nanometers, right? So if you wanted to create devices that were resonant in the optical range, you would typically have to make them on those characteristic hundreds of nanometers to microns dimensions. But if you use the surface plasmon mode for the same frequency close to this asymptote, you have wave vectors that can be orders of magnitude larger. So the corresponding wavelengths are effectively that factor smaller, right? So in principle, you could then take whatever optical phenomena you have over here at the micron scale and shrink it down to what turns out to be the tens of nanometer scale. It happens to be the skin depth of electromagnetic radiation in the metals at those frequencies. So the hope is that if you could take advantage of these oscillations, you could shrink optical devices way below the diffraction limit down to the nanoscale. So this has been exciting for quite some time, and in fact you can also show that these oscillations are fully quantized. So not only can you do optical devices, you can also do photonic devices. So whatever photonic phenomena you would ordinarily have to do at the micron scale, you could shrink that down to the tens of nanometer scale, the skin depth scale in metals, right? But the key challenge with using plasmons is that metals are extremely lossy. So when you try to do this oscillating electromagnetic field within the material, very rapidly you would dissipate energy to pairs of electrons and holes because you can excite these. And we will actually spend a significant amount of time worrying about how to calculate precisely this kind of excitation of electromagnetic waves in the metal to electron and hole pairs. Right? Now, from the point of view of doing optics or plasmonics in a material, this is a problem. You want to have the optical mode, the photon or the plasmon, as long-lived as possible. But this actually turns out to be useful from another point of view. If you could instead collect the electrons and holes that are being produced from this plasmon decay, you can use this as a very efficient way of absorbing light in very small regions in the nanoscale. So you could use metallic nanoparticles or nanostructures as nanoscale light capture devices, right? So what that requires, for example, you could have a modified atomic force microscope where you have these surface plasmons propagating along the tip, which then produces high energy electrons and holes which can inject into a material. So you could map out using this what the electron injection properties across this interface are going to be with high spatial resolution. And now you're limited by the skin depth length scale in doing this mapping and not the wavelength that you would ordinarily be doing if you did this with light and not with plasmons. And one of the things that was motivating our work when we started on this was applying the same technology for energy conversion. So there were these demonstrations where you could absorb light in nanoscale metallic structures, separating them into electron and hole pairs, which could then inject into catalysts and drive chemical reactions. So there was a demonstration that you could have this catalyst coated gold rods, which if you just put in liquid water, will start splitting water to oxygen and hydrogen when you shine light on it. Right, all with this plasmonic mechanism. So it's essentially a plasmonic photosynthesis unit. Now, the reason why there was a lot of interest in this area, or there still is a lot of interest in this area, is unlike conventional light absorption using semiconductors, metals do not have a band gap. They can absorb all photons in the solar spectrum, and potentially, if you do things right, you could use all the energy that's being absorbed to do useful work, like drive electrons to drive catalytic reactions and so on. But so far, the efficiency that has been observed has been quite low, on the order of 1%, substantially below what conventional semiconductor devices can. So what we set out to do is understand using first principles calculations, that is electronic structure calculations of the metallic materials here, what exactly are the limitations in harvesting plasmons and collecting their hot carriers, so that we could figure out how to overcome those bottlenecks. So I won't go into too much about that. I'll just give you a brief overview of what are the kind of things we can calculate. What's going on here? So let's start with a very simple picture of plasmon decay. So if I think about free electrons in a metal, I can think about them in terms of a quadratic dispersion relationship, energy versus K for free electrons. So this is just h bar squared K squared over 2m. The energy versus K relationship. And a metal would correspond to all electrons up to a particular Fermi energy field. Right? Now, if you want to absorb light in this material, you need to start from a state that is occupied and push this electron up to a state that is unoccupied. Okay. Now, in doing so, you have to conserve energy and momentum. So this energy difference between the initial and the final state is the energy of the photon, and the energy difference on the the difference in the x-axis, which is k, is effectively the momentum. Right? Now, in this case, because the photons are significantly faster than the electrons, effectively the momentum of photons in this axis is 0. So when you do this transition for momentum conservation, you have to go vertically on this plot, right? So if you think about a free electron metal like this, you basically don't have any transitions allowed. So pure free electron metal and infinite free electron metal cannot absorb light, right? Because there are no pairs of states that are conserving both momentum and energy with respect to a photon absorption. So let me pause here for questions. Does everybody get this so far?
Say it one more time.
Sure. So it's energy versus momentum, right? The length of this arrow along the y-axis has to be the energy of the photon h bar omega, and the distance in this direction should be h bar omega over c, that is the momentum of the photon. But on the scale of the electron momentum, that is practically 0. So to conserve energy and momentum, a photon absorption basically amounts to a vertical line.
Okay.
Right? And you can't fit a vertical line on that parabola such that one end is below the Fermi level and one end is above. Now, if you were in a nanoscale system instead, not in a bulk material, then effectively you are confining the electrons to some length scale, say on the order of 10 nanometers. So now momentum is no longer a good quantum number, right? Momentum ultimately comes from translational invariance. Once you've broken the translational invariance, it's no longer a good quantum number. With a very hand-wavy argument, I can say the momentum is no longer a precise value, but distributed based on the uncertainty principle. And as I make the confinement larger, I'm increasing the spread in momentum. So then effectively there is some finite probability in a nanoscale sample to do a vertical transition from the tails of these distributions. And I would expect that as I make the geometry smaller, the probability of this transition would increase. Right? So I would expect the probability of this kind of excitation to be inversely proportional to the dimensions of the sample. Right? Now, a better, more rigorous argument actually turns out in terms of orthogonality of wave functions. When you, so if you have plane waves of two different wave vectors in an infinite material, they are orthogonal to each other. But when you confine them to a finite distance, to a finite extent, then they are no longer exactly orthogonal. And that's what turns out to give you so this is essentially a selection rule, and that selection rule is slightly violated when you have a finite geometry. But regardless of which way you look at it, you will end up with the conclusion that your probability of excitation will be proportional to 1 over the sample dimensions. Right? Make sense to everyone? So at the time, the simulations that were around trying to understand what the limitations in plasmonic hot carriers were based on this simple idea, and they were using a free electron time-dependent density functional theory. And from that, I'm showing you a result from this paper over here. This predicts the number of hot carriers as a function of carrier energy away from the Fermi level. So compared to this plot, I'm looking at energy relative to this level. Right? So I can look at energies below which correspond to holes and energies above which are electrons. So what this plot is showing you is probability of hot carriers as a function of carrier energy relative to the Fermi level for spheres of two different diameters, 15 nanometers and 25 nanometers, and the y-axis is assuming a lifetime of the carrier as an unknown parameter. So it's saying if I could generate a carrier and it lived for 1 picosecond, this would be my hot carrier distribution, and so on if it happened to be up to 50 femtoseconds. So what you can see immediately here is in order to get high energy carriers, you both need to have a small particle, it doesn't happen here, and you need to have a high carrier lifetime. Right? Both of these things are important. Right? So you would need lifetimes on the order of a picosecond in order to have any significant probability of high energy carriers far away from the Fermi level that could do useful work. Right? But at this point, the key issue is you are completely neglecting the actual electronic structure of the metal. The metal is being treated purely as a free electron gas, which we know it is not. And we are not necessarily accounting for additional mechanisms, and if there are additional mechanisms, what their relative contributions would be. And all of these could change differently depending on the size of the material, right? And most importantly, the lifetime was an absolutely critical component of whether this was a useful scheme overall, right? And that is so far an unknown input, right? Which is being varied by orders of magnitude, and it needs to be in a certain order of magnitude for hot carriers to be viable. Right? So this is what we wanted to answer. So let's start by looking at the possible mechanisms when you switch from a free electron material to a real material. So what I'm showing you here is the band structure of gold, which is still energy versus momentum, except this is a funny momentum axis. Right? So this is the Brillouin zone in reciprocal space of gold, and gamma corresponds to k equal to 0. So instead of just going in one direction away from k equal to 0, in order to sample everything in this three-dimensional space, you go along this path. Right? And so then that's kind of unfolded, and you're drawing energy versus a one-dimensional k axis here. So is everyone familiar with band structure plots, or do you want me to pause here for a little bit more? Yeah, question? Okay, all right, so let me explain that, thanks, I'll explain that once more, right? So in the case of the free electrons, we are looking at energy versus momentum, and that was the key quantity that allowed us to make the arguments that we did, right? We need to conserve energy and so on, so we have to do all of those same things. Now, if we want to think about this real material, you have to think about the energy versus momentum, with momentum being a three-dimensional vector. For each possibility of that three vector of momentum, you have multiple possible states with different energies and velocities and so on, right? So what this is showing you is the energy versus momentum in this three-dimensional space, but if you have to represent that full thing, that would require a four-dimensional plot, so that would be really difficult. So instead what you do is you pick a segment through all the important points in the reciprocal space of the material, right? So that's the segment, and then you unwind that over here. So this corresponds to k equal to 0. Then you're moving along one direction, and then along the surface of that zone and so on, coming back to k equal to 0 and so on. So you're able to represent all the relevant points once again. And if you notice, you do see some segments which have this parabolic characteristic very similar to what you had for the free electron metal. So that corresponds to the free electron-like electronic bands within this material. But now additionally you have all of these extra states that come here because this is a real metal, and specifically in the case of gold, these happen to be due to d electrons in the material, right? So once we set that up, the rules that we laid out before are exactly the same. You need to conserve energy and momentum. So if you want to absorb a photon, you need to match the length of the arrow here, right? You need one state to be below the Fermi energy, which is up to which where the electrons are occupied, and you need the final state to be above, right? But now you can see that you do have, if your arrow can reach from this point to that point, you can satisfy energy and momentum conservation, and you can absorb light directly by doing that. Right? So these would be called direct transitions, and they start at the d electronic bands of the metal and end up in the conduction band, which are more s orbital like. And like we discussed before, you have these geometry or this momentum uncertainty assisted transitions. So in this free electron region, for any length of this arrow or any photon energy, you could still do that transition in a nanoscale geometry with probability proportional, inversely proportional to the sample size, as we discussed before, right? But in addition, when you have a real material which has atoms, you can have quantized atom vibrations or phonons, and phonons turn out to have very low energy compared to the photons, but they can have momentum comparable to the electrons. So effectively, you can now do transitions where you can borrow the momentum from the phonon, and you can borrow energy from the photon to do this transition. So you now have two ways of doing, so you can do vertical transitions and you can do non-vertical transitions, either based on the geometry or based on taking momentum from lattice vibrations, right? And up until now, it was basically only this mechanism that was considered in the study that I showed you. Yes?
How do you define the order of these points, from gamma to x to w to l and back to gamma and to k?
Mm-hmm.
How decide this order?
So this order is essentially arbitrary. So you could, for a given material, you could choose any path you want. This is basically, the more points you put here and the more segments you do here, the better, because you're capturing all the possible points in the in this Brillouin zone. Ultimately, any quantity that you calculate will be integrated over this entire volume. So this will not be used for any calculations. It's only used as a way of representing it in a low-dimensional plot. That makes sense, right? So for any given material, you have some standard choices for high symmetry points and high symmetry paths, but there is a lot of arbitrariness in the order and the connectivity. Any other questions so far? So now to calculate this, and this is what we'll work at. Oh, I forgot to do one more thing here. And if you want, if you're familiar with Feynman diagrams, you can summarize these processes quite easily as shown here. Effectively, the direct transitions is a photon coming in, giving you an electron hole pair directly. The phonon assisted transition is a higher order process where you have a phonon and a photon connected by an intermediate electron line, and finally you still get back an electron hole pair. And this phonon with the dashed line could either be absorbed or emitted. How many people here are comfortable with Feynman diagrams, perturbation theory? Sort of. Okay, great, yeah.
About the solid line with the arrow there, I understand there are two carriers with different charges, like arrow and the hole, right?
Yes. Yeah, yeah. So instead of electrons and positrons in vacuum QED, you'll get electrons and holes here. Yeah. Yeah.
Can you conserve the energy and momentum in the first
Here? Yes, because you now have these additional bands. So in the picture here, you only had a single band, so you could never connect a vertical line across it. But now, because you have multiple bands, you do have possibility for vertical lines. Just there is a minimum photon energy, I think somewhere over here, which is required in order to do that transition. If you're below that threshold, then you're forced to do one of these, which are allowed for any energies. So that threshold is called the interband threshold energy. And I'll show that to you in the results in just a moment. Any other questions? Okay, yeah.
On the geometry of this state process, so what's the mechanism?
This is basically the one that we were talking about, what we were discussing here. So when you take a finite geometry, you no longer have the selection rule in a bulk material exact. So with a small probability in a sample size dependent way, you get non-vertical transitions. So this is basically what I'm calling the geometry assisted transitions in that diagram. Anything else? Okay. So this is what we're going to work towards. We'll not do all of this in the Python exercises. We'll build on the simpler ones here. But basically what we need to do to capture this entire picture is to do plasmons on the higher length scales. We need electromagnetic simulations. And basically that give us the photon energies and the matrix elements for coupling photons to, it gives us the electromagnetic field profiles. On the lower end, we have density functional theory, which we'll discuss briefly, which gives us the electronic band structure, as I showed you here, and it gives you the matrix elements for coupling electrons to light and to phonons. And by doing another version of density functional theory, you can calculate phonon band structures, which are these lattice vibration modes, and the coupling of the electrons and the phonons. So effectively, these band structures and these coupling matrix elements correspond to knowing all these propagators and these vertices. And if you know them, you can put them together to calculate arbitrary diagrams in perturbation theory. Right? So you could calculate things like the phonon assisted transition, which will then evaluate to in perturbation theory an expression like that. Right? We probably won't do that one. We'll probably focus on the simpler ones here. But the challenge doing these directly from this quantum mechanical calculation technique of density functional theory is that it takes a lot of time calculating these matrix elements. Right? Calculating these electron phonon matrix elements you could probably do on the order of 10 to the 5 per characteristic core R of a computer, which sounds like a really high efficient thing, except that to converge these types of processes, you need to account for around 1 trillion of these matrix elements. So that becomes extremely slow. So the idea of what we're going to talk about here are these ab initio tight binding models, which allow you to take these ingredients from density functional theory and interpolate them in K, and then evaluate these quantities at a much higher throughput, typically on the order of 1 billion matrix elements per core R. So we'll be able to compute some of these processes in a few minutes here, which if you were to do directly from DFT, you would have to spend hours or days doing. And some of these processes you simply could not do unless you had this kind of a technique. Right? So this is what we're going to spend most of the time here on, and we'll focus on some of these simpler processes and also other electronic structure properties that are not directly related to hot carriers, just to get warmed up with that. Right? So just to give you a feel of what we could do with this, we can now calculate as a function of particle size all these different mechanisms that I showed you, as a function of plasmon energy and the relative contribution. So you notice that so I'm showing you this for a bulk surface and gold spheres of 40, 20 and 10 nanometer sizes. So if you are at a plasmon energy above 2 eV, this is the characteristic energy above which the direct transitions are allowed, then immediately those dominate and account for about 90% of the transition rate. But when you're below that threshold and you're forced to do when you're not able to do the vertical transitions, then you have to do these indirect transitions, which are either based mostly on the phonons, and this resistive is basically another phonon effect in the bulk material, or you can have these geometry effects which increase in magnitude as you make the particles smaller. Right? So in the bulk surface, you have very negligible geometry effects, mostly direct and phonon based processes. And as you make the particles smaller, those uncertainty principle based contributions increase till they become dominant below 10 nanometers in size. Right? Also, moreover, we can add all these contributions together and predict the total line width, which corresponds to the plasmon decay rate, or effectively the dielectric function of the material, and compare that to the experimental value. And once we put all of these mechanisms together, you actually find pretty good agreement for all these four metals, which are the most promising plasmonic metals. So aluminum and the three noble metals. Right? So effectively this shows us that we've accounted for all the dominant mechanisms of light absorption in these materials. Right? But so far we have basically just matched experiment. We've given some insight here about the relative contributions, but the real power of this approach comes in looking at the carrier energies that are resulting. So what I'm showing you in these plots is the probability of generating carriers with a particular frequency and energy. With carrier energy on this axis, holes on this side, electrons on that side, this is the Fermi level. Going into the plane of the page is the photon energy, and this axis is probability. Right? The color scheme is showing you the ratio of indirect transitions, which is phonon plus the geometry, and the direct transitions, which is the vertical arrow. Right? So as in the previous slide, so basically low energy infrared plasmons are close to you, and visible and ultraviolet are at the back end. Right? So you see these red plateaus over here. These basically correspond to a uniform distribution of carriers ranging from 0 to the plasmon energy. And this is the result of these indirect phonon-assisted transitions. They give you a uniform carrier distribution. But the moment you go to an energy on the order of 2 eV in gold, similarly 2 eV in copper, and about 4 eV in silver, you switch from this red plateau to these blue hills. Right? And now they are extremely sensitive to the electronic structure of the material. Right? It's no longer a uniform probability distribution. There are certain peaks here depending on where you have electronic states available. So specifically in both gold and copper, you get high energy holes far away from the Fermi level and relatively lower energy electrons. So effectively, if you were thinking about a device with semiconductors, these holes would be able to inject into a p-type semiconductor more easily than these electrons could inject into an n-type semiconductor. Or if you were doing chemistry with this, you can more easily drive oxidation reactions using these holes compared to reduction reactions with these electrons. Right? Silver, on the other hand, is more balanced, where you have the energy distributed across the electrons and holes for all of these energies. And aluminum is weird that it mostly has direct transitions, but it still has a uniform probability distribution of carriers. And this happens to be because this corresponds, even after these interband transitions, this looks like a free electron metal. So there isn't electronic structure which is focusing states at particular energies. It's sort of equally distributed across the spectrum always. Okay? And we'll focus most of our calculations on aluminum in the examples that we'll do next.
Sorry.
Yeah.
This is carrier aluminum.
Yeah, so it's plasmon energy into the plane. Yeah, yeah. And basically energy conservation is giving you these lines because you can't, but with some small probability you can go beyond again due to the uncertainty principle. So these plots account for the finite lifetime of carriers as well. So you can create extremely short-lived carriers above the energy of the photon.
So are these just scales or the negative values of energy gain in something?
The negative energy corresponds to holes. So 0 is the Fermi energy. Yeah. Thank you. Yeah.
Plasma energy. So what does it mean by plasma energy?
The plasmon energy. So you can also think about it just as the photon energy. So you have a photon in free space which excites a plasmon in the material, which then decays. So the plasmon has a characteristic frequency, and its corresponding h bar omega is the energy that we're plotting here.
So it's coherent energy with the plasma.
Yes. So the photon and the plasmon will have the same frequency and the same quantum of energy that can create these electron hole pairs. Yeah. Any other questions? Okay, the last few slides here. Let me just check on the time. Okay. So, all right, so if you wanted to think about the grand scheme of what one would need to calculate in order to understand these hot carrier processes completely. So you have light excitation on these nanostructures with this golden egg shown here, which excites plasmons, right? I'm using the Feynman diagram notation of bare and dressed propagators to represent photons and plasmons here respectively, for those who get that, right? And then these plasmons can decay to electron hole pairs due to a number of mechanisms that we briefly discussed, but that's only the first step. Then those electrons and holes that have been produced within the material need to get out either to the surface of a semiconductor or to some molecule absorbed to drive some reaction. Right? So the other important point is the transport of electrons and holes, but these are not near equilibrium transport. This is a non-equilibrium transport problem because you have these energy distributions which are very far away from the thermal distributions once they have been excited by electrons and holes. So you need to understand how these high energy carriers transport through the material. Oh, and by the way, when I say high energy carriers, I just mean here high relative to the thermal energies, right? So I'm talking about carriers with energies on the order of a few electron volts. Yeah, I know high energy can mean completely different thing for people here, right? So yeah, and then you have these transport, and so you need these electrons and holes to eventually reach the material. So we also need to calculate this part. Right? And so that you can do by using the Boltzmann equation, and the collision integral that goes into the Boltzmann equation can use the rates calculated quantum mechanically for these electron scattering processes. So we'll do a little bit of that, at least in some specialized cases. We'll probably consider an example of electron phonon scattering. So anyway, if you were to calculate all of that, for the same four metals, I'm showing you here the lifetime versus energy away from the Fermi level. Okay, the red, so the lifetime is on the left axis and shown in red, and the dark blue is carrier mean free path on the right axis in nanometers, right? So you'll notice one common pattern for all of these. I also notice that the characteristic velocity in all of these materials is roughly the same. That's why, and they're all on the order of a few nanometers per femtoseconds. That's why these plots kind of coincide. So what you find here is the highest lifetime and mean free path is always at 0, which means carriers at the Fermi energy, right? And here it's predominantly due to electron phonon scattering. As you go away from the Fermi level, the electron phonon scattering contribution remains roughly constant, but you have a new mechanism which is electron-electron scattering. One electron can give its energy to another electron in the Fermi sea and produce an electron hole pair, a new electron hole pair in the material. And the number of ways in which you can do this increase as you have a higher energy. So you have a greater phase space for scattering, which increases your rate and decreases your lifetime. And this goes quadratically as E minus EF squared away from the Fermi level. So you basically have a constant and an E minus EF squared contribution, which gives you this overall profile. Right? In addition, you have electronic structure effects. These are again the d electron bands in the noble metals. So when you access these new bands, which are no longer the free electron bands, you get some deviation from this nice smooth structure. Right? Now, the other thing you'll notice is that there's a significant spread. There's not a single number at a given energy. Any guesses as to what causes that? Why is there not a single lifetime or a mean free path associated with a given carrier energy? Sorry, say that again?
They always appear or be eliminated by the pi.
Sure. But for a given electron, so yes, they will always be produced in pairs. They will always annihilate in pairs, sure. But right now we are looking at the properties of the individual ones, right? So the question is just for a given electron energy. So this is being plotted just for a given one. So you can ignore the other particle for now. Why is there not a single number but instead a distribution? So these are predictions for an infinite material, and in fact all the things we'll do in the next couple of days are going to be for an infinite material. Yeah.
This
maybe due to the asymmetries in the actual material?
Very good. So it's actually an anisotropy of the material, right? So all directions in the material are not equivalent. These are electrons moving in a crystal. So at a given energy, if the electron is moving in different directions, it has very different electronic properties. So electron energy alone is not enough to quantify the, to completely describe the state. You need to describe it in terms of a wave vector and a band, as we had shown previously. In fact, if you look just at energy equal to 0, which is the Fermi energy or the Fermi surface, you can look at all the states that have that energy. That gives you the Fermi surface. That's what I'm showing you here. Right, so on this Fermi surface now, so the noble metals, copper, gold, and silver have this kind of shape. Right, the electron phonon scattering time is highly anisotropic. In fact, the very interesting thing that we found is that there seems to be a correlation between the scattering time and the curvature of the Fermi surface. So where you have a positive curvature versus a negative curvature, you have the minimum and maximum of times, varying by almost a factor of 2. So all of this again has to do with phase space. It has to do with how many pairs of electrons are available that conserve momentum with a phonon and give you the appropriate and also conserve energy, right? So those number of states changes depending on whether you have a positive or a negative curvature, right? So this factor of 2 to 3 spread at a given energy due to anisotropy is what is showing up here. Does that make sense to everyone? Okay. So that's the end of the brief results that I wanted to show you. Before starting with the code, I'll just give you some of the theoretical formalism that is necessary to do the code exercises. So we'll talk briefly about density functional theory here, but I won't dwell on it much because you're going to do that in detail in a module tomorrow or day after, I believe, right? Or maybe later this week. I forget when I suspect, yeah, I think later this week. So you'll have a detailed module on density functional theory. So what I'm going to do here is I'm going to take the quantities that come out of DFT as a given. Those inputs are already packaged and given in the files in the Dropbox to you. We will only do the post-processing starting from there. And all the details about density functional theory that go into calculating such things, you will learn later in the module. Okay, so from the point of view of what we need to know here, right? So you have electrons in a solid. The electrons in the solid are described by wave functions that have a wave vector k and a band index b, right? Within this cone-sham DFT, each of these states satisfy a one electron Schrodinger equation, right? Written in this form. It's only slightly different from what you might be familiar because of this plus ik, and that's coming from this periodic block phase that I've taken out of these wave functions, right? And then the potential that's there in the Schrodinger equation is an effective potential that's due to the nuclei in the material and all the other electrons. So it's effectively a kind of mean field theory, and that potential depends on, yeah, as I was showing you here, it's the nuclear potential plus it's the mean Coulomb field of all the other electrons plus some corrections which are called exchange and correlation. All of these depend on the electron density here, which is calculated from these wave functions. So effectively what DFT does this in a loop where you have a guess for the electron density, you compute the potential, you solve the Schrodinger equation for all the states. From that you compute the electron density, recompute the potential and make this self-consistent. Right? So eventually you have an approximate representation of the quasi-particle states in the material and their corresponding energies. Right? And what we need to know here is that all of these are going to have a wave vector k and a band index b. Right? Similar to the plots that we had, right? So if I just to reference that, so this is the wave vector k, it's actually a 3-dimensional index, right? We are plotting that along a 1-dimensional coordinate here, but when we are calculating, we need it as a 3-dimensional index, and all these different branches that are present here are indexed by that band index b. Right? So that's an integer, and k is everywhere in that Brillouin zone, inside that. Okay, and because electrons are fermions, these occupation functions that go in here are going to be Fermi functions with some chemical potential mu. Right, which is basically controlling up to what energy the electrons are filled and beyond which the electrons are empty. In the limit of 0 temperature, everything below mu is exactly occupied, F equal to 1, and everything above mu is exactly unoccupied, F equal to 0. Right? So, as I discussed before, in order to calculate what we are going to calculate, we are going to need a very large number of k values on the order of 10 to the 6 to 10 to the 9 in order to get good convergence of the properties you're going to predict. But for conventional DFT calculations, it's typical to not use more than, say, 10 to the 3 or so of these k points. So that's where we need this new technique to bridge the to bridge what we can calculate with nk on the order of 1,000 to something that requires convergence on the scale. All right? So that's where Warnier functions come in. So what Warnier functions do are they are effectively a unitary transformation of these orbitals. So remember that these orbitals have two indices, this wave vector k and the band index b. The unitary transformation is happening in both of these spaces. In the space of k going to r, this looks basically like a Fourier transform. In addition, there is a unitary matrix at each k that rotates the band index. Right? And that gives you new wave functions which are indexed by r and this new index a. And the property that is unique to them is while these original functions were periodic in space, these new functions generated this way are localized. They are specifically localized around the site r. And more importantly, as you go away from that location r, these Warnier functions will decay exponentially. Right? So this doesn't yet tell why they are useful. We'll talk about that on the next slide. Now, procedurally, what you do is you optimize. So these unitary matrices, these U matrices are free parameters. In Warnier function generation, which again we are not going to talk about here, you optimize these matrices to make these Warnier functions as localized as possible. So regardless of what unitary matrix you pick, these Warnier functions are always going to be exponentially localized. Right, they're going to decay exponentially away from a lattice site, but you can increase how exponentially they decay by optimizing these unitary rotations. Right? And when you maximize that, they're called maximally localized Warnier functions. And with this unitary transformation, you can very easily show that the inverse transformation takes roughly the same form. You just change the sign of the Fourier transform and you take a Hermitian conjugate of that matrix. I think there should not be a 1 over nk here, so that's a typo. Yes?
So in the first equation, you already sum over the k.
Yes.
Then what's the 1 over nk?
In reality, this is, if you were to think about this continuously, this will be an integral over the Brillouin zone with decay. So this 1 over nk times sum over k is a discrete Fourier transform. So you're picking a uniform mesh of k, and this 1 over nk is just the number of k's that are present in this sum.
Oh.
Yeah, sorry, that's what you're asking. Yeah, nk is the number of k's that are present within the Brillouin zone. Yeah. So thank you. Okay, so effectively this is a Fourier series and a discrete Fourier transform and inverse discrete Fourier transform between k and r, going from periodic functions in space to localized functions in space, right, with the easy inverse transform. Right. Now, why these are useful are what we're going to come to here. So let's now think about an arbitrary operator whose expectation values you might be interested in. We are going to work with two in particular. We're going to think about the electronic Hamiltonian, which will give us the electron energies, and we are going to look at the electron momentum operator, which is going to give us the coupling between electrons and the electromagnetic waves. Right? So if I take an arbitrary operator O, I can define its expectation value this way by taking its integral across these orbitals, right? Now the point is, if I now consider my unitary transformations here, oops. So if I look at my unitary transformations here, I can bring that. I could rewrite these. I could substitute these orbitals in terms of the Warnier functions, and I could rewrite this in terms of the matrix elements expectation value in the Warnier basis. Right. So plugging those unitary transformations in here, I can rewrite this in terms of the R minus R prime and these Warnier centers instead of the original band basis. Right. So I effectively originally have an expectation value for this operator O at each k across all pair of bands B and B prime. That's present here. I'm doing this unitary transformation on both sides of this operator to get it to the Warnier basis, which gives me a matrix element across two different positions R and R prime and across two Warnier centers A and A prime. Right? Now this in itself is not a particularly useful quantity, except that you have exactly the same sort of inverse transformation here. Right? And it allows you to calculate this expectation, you calculate this operator once again at any k, but now you are no longer limited to calculate this at the same k that you started out with. So you could do this transformation using a very few k points, like the 1000 that you had. And then after you've computed these localized matrix elements, you could do this inverse transformation and you could compute this for an arbitrary number of k very quickly without having to do that Schrodinger equation solution. So let me repeat that. The key point here is you calculate the original orbitals and eigenvalues and everything for a few k points here, which you do in the original electronic structure calculation, for which you have to solve the Schrodinger equation, which is expensive. From that, you calculate the expectation value of any operators that you're interested in. Take those operators and convert them to this localized Warnier basis. Right? And because of the localization of the Warnier functions, these are going to be short range. So you don't have to keep a very large number of R and R prime. They're going to exponentially decay as R minus R prime gets large. Right? So it's going to have a, so if I think about one R being here, the range of R prime will be something on the atomic scale around it. And then once I have that short-ranged matrix elements, which I computed from say 1000k, I can recompute them for any k I want here. They don't have to be from that original set of 1000. And effectively what this is doing is interpolating these operators across k. Right? So effectively what this is doing for us is it's giving you a physically motivated interpolation on that Brillouin zone. So effectively you had a few points on this polyhedron for which you actually calculated the properties, and then by doing this transformation you're able to continuously sample everywhere within this at a much higher computational efficiency than repeating the quantum mechanical calculations at each point. Okay, so any questions on that? I mean, this should become a little bit clearer as we start doing this in code. So this is what we're going to spend the rest of the time doing, starting with the electronic states, and then hopefully at the end of tomorrow we'll do something with electrons and phonons. So any questions about this so far?
In order to get some properties at specific high-symmetry points, you still need to do integrations over all the Brillouin zone. So, I mean, you still need a sample of k points in the Brillouin zone, a large number of k points.
So so when you're doing the density functional theory calculation, you need a certain number of k points to converge the density and so on. But that is usually a much fewer number of k points than what is necessary for calculating properties like optical excitations and so on that we're going to consider. Right? So the point is we will do the DFT calculations with very few k points. I mean very few meaning still on the order of 1000 to few thousand. But then we will be able to compute these expectation values on millions to billions of k points in about the same time. Yeah, right? Okay, so what I'm going to show you here is coming from this density functional theory code that our group maintains, which is called JDFTX. And it has special features for doing all of these Warnier toolkit calculations. We are going to use results of calculations from here which are already going to give us Hamiltonians and momenta and so on in this Warnier basis. So we are not going to cover the calculation of these quantities in the Warnier basis. If you're interested in that part of it, it's actually covered in the tutorials on the website. But those will have more software issues getting the DFT program installed and so on. So in the interest of time, we are going to focus only on the post-processing where we actually build up the code from scratch in Python. Okay, so I'm going to give you some text files and binary files and describe their format, and we're going to start working from them. All of those files were generated as described in these tutorials, right? Okay, so let's probably take a short break, say 5 minutes or so, and continue from there. In that time, so in the Dropbox, there are two Python notebooks. There is it's called Carrier Dynamics, and then there's a Carrier Dynamics -Skell. So that's so basically the let me show that to you here. Right? So this is the completed notebook where everything is already worked out and the code and the results are all there. And the skeleton version is where I've stripped it down, and I'm going to sort of build up from that here. Right? So it will have just the text descriptions in between, but it won't have the actual code.
And that's what you want us to do? We'll be working with that first?
So I will be working with the skeleton, but you could follow along either with the skeleton if you're building in the code, or you could look at the completed one if you needed to fill things in. And oh, Natalia just left. And often I'll forget what I was doing, so I'll ask someone to look at the regular one and help me fill in the gaps if I've forgotten. Okay, all right. So at say 4:20, we will pick back up. We have about half an hour now, so we'll maybe talk about just the first section here today, which is we'll take the Hamiltonian operator interpolated into the Warnier basis, as I just discussed. So we'll come back to that with a little bit of detail here, and we will make those band structure plots this time for aluminum using just that information. Right? So that's what we're going to do here. And then we'll gradually build on that and calculate other physical properties. So this is going to be on one of those high symmetry k-point paths like we had shown. So I'll read in a particular path and plot the properties on that. After that, we are going to do integrals on the entire Brillouin zone, and we will use Monte Carlo sampling to do those integrals. Right? So that will start with the density of states section. So we are going to look at the plasmonic metal aluminum, which has a face-centered cubic structure. And the Warnier tight binding files are all these MLWF, etc. files that are there in that directory. Right? So one of them is a text file. This cell map is a text file, and let's look at its contents. So this first set of lines here is just equivalent to the head Unix command. So I'm just going to print the first 5 lines of this file. So I'll also just give a couple, especially for those of you on Windows, just let me know if the overall things are working, because I heard from previous modules that there were some incompatibility issues with that. So if you can confirm that like the basic first few things are working, then we can go forward. Yeah, good. Okay, so this is what the file looks like. So this contains a list of I0, I1, I2, X, Y, Z. So these are integer lattice combinations. So these correspond to the R minus R prime that we were talking about in the Warnier basis. It's basically telling me that I have one Warnier function at a particular location, and I'm looking at the matrix element expectation value to another Warnier function at a relative displacement. Right? It doesn't matter where the first Warnier function is by translational invariance of the crystal. It only matters what the distance between the displacement in terms of lattice units that are present for the two Warnier functions. Right? And so these are the displacements in terms of the lattice basis of the crystal. So if you were thinking about a cubic lattice, it would just be this multiplied by the cubic lattice constant in each direction. and these are the Cartesian offset directions. Okay, so these are the actual positions in Bohr units. So in terms of hydrogen radii. So all the outputs of the code are in atomic units. So energies will be in Hartrees, that is 27.2 eV, and distances will be in Bohrs, like 0.5 angstroms. Okay, so now notice that this is not exactly a multiple of that, because this is not a cubic lattice. This is actually a face-centered cubic structure. So the bases for the lattice vectors are not orthogonal. Right? So that's one, we won't have to deal with that complexity for most of what we're doing, but just something to be aware of here. Right? We'll deal with that a few times total in this lecture. Okay, so first what we are going to do are pick up these two data sets separately. So we're going to get an integer data set, which are these integer lattice combinations, and we'll get these floating point numbers, which are the Cartesian offsets. Right? So I will first read in all the data using load.txt. This is a simple text file which just has tab separated data. Right? Then I'll pick up the lattice coordinate stuff, which I'll just call cell map, which is going to be cell map data, all rows and the first 3 columns. And I'll have the Cartesian part of it, which will be that all rows, last 3 columns. Right? And so what you find is we have some 2400 odd cells, and of course we get back the cell map and the integer combinations and the Cartesian coordinates here. Also note that this one happens to be floating point because the overall data set was float. If we wanted to make it integer, we could do it this way. Okay, so these, as I mentioned, these integers are basically the linear combinations of the 3 lattice vectors that specify the crystal. And in this particular case, those 3 lattice vectors are not just x, y, and z. Right? This is a face-centered cubic lattice. It has a different basis. I think this is my first question. So I'll start with this simple question. Using the information that we have so far, can we reconstruct what the lattice basis is? This is just a Python warm-up exercise. So I have these 2 data sets which are giving me these integer combinations, and it's basically these integer combinations of the columns of some matrix give me this matrix. So I have a n cells by 3 matrix here, and one more n cells by 3 matrix here. From this, can I reconstruct the 3 by 3 matrix that's relating them? What would be the easiest way to do that? Yeah.
You could take the inverse of the matrix, the first one that you have, multiply by the second.
How would you invert the n by 3 matrix?
That's the product of these. These are both column matrices, right?
They both have dimensions n cells by 3.
Solves the set of linear.
Okay.
The fact that the set of equations is overdetermined doesn't get a problem, right?
It should not be, if we do it correctly.
So
Yeah.
that is n cross 3 and this is n cross 3. You drag the transpose of one of them and take the tensor product then. That will give you a 3 cross 3 matrix, right?
But that's not the, so we basically have, if we call this matrix A and this matrix B, we have A times X is B. So there is some inversion that needs to happen here. So it's not a product of these two. we kind of have to invert one of these. We basically have to invert this and multiply by that, but that's not a well-defined operation. So how would you, in code, how would you do that, what you're describing?
So what do you mean by it's well defined, just because it's not the same dimensions?
So are you talking about like you'll construct a pseudo-inverse or something?
Yeah. I mean, so what I would do probably would be to dimension part, like you said, by the reciprocal of the dimensions. So like you have a 3 by 2 or something, do a dimension product by a unitary matrix or something like that.
Okay, it would get, as you can see, if you actually try to write that, it gets fairly complicated. You can't inverse it, but there is a NumPy function that will do all of this in a single line. And the key point is it's an overdetermined system. So you can invert this, so you can't invert this matrix, but you can solve the system of equations in a least square sense, right? So effectively all you need, and this was covered, least squares fitting in NumPy was something that was covered in one of the earlier modules, right? In one of the tutorials. So effectively all you need to do is it linearity.least squares? Maybe, but we'll come to that in a second. So we are trying to invert the first, we are trying to invert the integer matrix, which is cell map, and then we are basically trying to multiply the inverse of cell map with each column of the Cartesian cell map, and that should give us the basis vectors, right? And this least squares function in NumPy automatically handles multiple right-hand sides. So this is going to do the least squares problem for each row in cell map, or each column in cell map cut separately. So this should already do what we want. Now it's linearity.least squares. It's LSTSQ, right? Isn't it? Just suppress that warning and I'll just look at the first entry. Okay, so I get a 3 by 3 matrix by doing that, and these actually happen to be the basis of this lattice, right? So it's basically 0, a by 2, a by 2, a by 2, 0, a by 2, and a by 2, a by 2, 0. So those happen to be the basis of the phase entry. Yeah.
Can you explain one more time what that function did? You were saying it took it inverted the integer matrix and then we multiplied that to each.
Yeah. So this is basically solving the solving cell map multiplied by R basis equal to cell map cut in a least square sense, because it's an overdetermined system. Technically, because these are supposed to be in columns, this is supposed to be the transpose. In this particular case, it doesn't matter, but yeah. Because for each column of 3 combinations, R basis is supposed to be on the right for the coordinate transformation. That doesn't matter for this example because it's symmetric anyway. Okay, so that gives us the basis vectors. So it's the linear combinations of these that give us that, and we can check that this is the case. We can look at what the error in the we can check that this is actually fully determined. We can do look at the difference between cell map Cartesian and this matrix product. And you can see that's basically 0 to numerical precision. So the system was exactly satisfied. Because there's of course no guarantee that for a general set like that you're going to get all the equations exactly satisfied. Okay, right. Now coming back to this, For those of you who are familiar with tight binding models, these are basically simple Hamiltonians that can reproduce your electronic structure, where you account for interactions between one lattice site and the next, the nearest neighbors and the next nearest neighbors, maybe on the order of a few tens of sites around the central point. If you look at the number of cells in this Warnier expansion, it's a couple of thousand. Right? So while these are termed tight binding Hamiltonians, these are actually accounting for the interaction between the electrons over quite a decent range compared to the next lattice site. So in particular, this Hamiltonian was generated from a DFT calculation which did a 12 by 12 by 12 sampling of that Brillouin zone. So effectively, this is capturing interactions up to 6 lattice sites away in a Wigner site cell shape on the thing. Right? So with some symmetry additions and so on, that turns out to being this 2400 sites around that. So because of this, what you get in this Warnier Hamiltonian is an exact reproduction of all electronic properties if you were to recalculate it at specifically the K points that you calculated, but it's an interpolation everywhere in between. Whereas if you were doing a conventional tight binding model, you will be fitting and throwing away a lot of data, and you won't be able to capture the band structures and so on exactly. Okay? Okay, so next, if I want to calculate the reciprocal lattice vectors from this, how would I do that? The basis for the reciprocal lattice vectors. Very good. So this would just be 2 pi times the inverse of that, and there's also a transpose. But again, that doesn't matter in this particular case, right? And for those of you who know, this happens to be the set of basis vectors for a body-centered cubic lattice, because the reciprocal space of face-centered is body-centered and vice versa. Okay, so after that warm up, let's read the Warnier Hamiltonian. This time it's just a flat binary file, and we have to figure out its dimensions and reshape it into the appropriate form. So it's going to be a file which has contents whose dimensions are number of cells, which correspond to the number of these neighboring sites, times number of bands by bands. Right? But we don't yet know what the number of bands is, so we are going to do this in 2 steps, or a few steps. We are first going to read the Warnier Hamiltonian, and that just amounts to this. If you run that, you just get a list of numbers. Right? From this, I can, knowing what the dimensions are supposed to be, I can see that the n band squared should be that, and from that I can determine and with that I should be able to reshape this . Right? And there's one other subtlety, which is that there is a difference in data order between what's used internally in JDFTX and Python. So I have to swap a couple of axes. So this has to do with the data being stored row major in one and column major in the other. Right? So if you do that, then you will get an object which is a 5 by 5 matrix, so that's the number of bands for each of these cells. Right? So going back to the presentation, this 2449 axis is the R minus R prime, and the 5 by 5 are the A and B indices. So this has been done using 5 Warnier centers or 5 Warnier bands per unit cell. Right? And so I get a 5 by 5 matrix for each separation between lattice vectors. Okay? Everyone able to run the code so far, including on Windows and Mac? For those who have it, awesome.
What does that? I understand there's going to be a set of matrices you said, but like, is it very dense or is it very sparse?
So if I think about the Hamiltonian in the final K basis, in the basis of K vectors, it is diagonal in K by the that's basically Bloch's theorem, right? That you don't couple K and K prime by the electronic Hamiltonian. In the Warnier basis, it is not diagonal in R. It has a finite range in R which has to do with the Warnier function localization. So effectively, now this of course is in some arbitrary order as specified in the cell map, but for any point in the crystal, it's telling you what the Hamiltonian is for a given separation. And it is sparse, but in this representation that you have already chosen, it is dense. It is sparse if you were to list out all possible cells. Right? So for all practical purposes, we will have to work with dense matrices, which in a way is good. Okay, so now for our specific band structure example, we are now going to read a K-point path. So let's look at this file that contains the K-points. So this is just a list of fractional coordinates. These are now in the basis of reciprocal lattice vectors, telling me those high symmetry K points, and these are the corresponding labels like gamma, X, W, L, and so on. And for making a band structure plot, I just have this path index on the right hand side, which is telling me roughly how many points I should put between gamma and X when I'm making my plot. Okay? So let me separate these out here. So I'll first read the high symmetry K points here. This will be and I can pick out specific columns by doing this. I can similarly pick out the index by looking at column 4 and the labels by looking at column 3, except that by default load.txt will only work with numeric data sets. So if I have a non-numeric, this should also be a list, so I need to do that. To do a non-numeric data set, I have to explicitly specify that I'm going to load strings. Right? So you can see that this, what you're going to get at the end of this is a path that was what I was showing you, which is it comes back to gamma at some point and goes to other symmetry points. Now, as somebody asked, this is arbitrary. I could choose another K-point path as long as you have enough information to cover all the high symmetry regions of the Brillouin zone. All right. Now, this code is kind of not particularly insightful, so I just have it here. I didn't fill it in from scratch. So all I'm doing here is I'm starting from this list of K points, and I'm creating a path which connects from each K point to the next one in the interval with the number specified by what I have here. Oops, this I need to also specify the type here to make sure that it's an integer. Right? So effectively all I'm doing is I add in the first K point, then I loop over the intervals, and for each interval I create an X value which is just goes from 0 to 1 with that many points, and then I compute the K points by a linear interpolation. It's the initial point in the interval, difference between the points in the interval multiplied by that X. And then I put all of those together to get the final K point path. So I'll have, for that 178, I'll have 179 total K points, which goes from 0, 0, 0, which is gamma, up to 0, 1/4, 1/4, which is x, then goes to the other k points and so on. Right? So this code just constructs that explicit list of k points starting from the specification in that input file. All right? Okay. So now let's get to the main point here. We want to compute the energies based on the Swanee Hamiltonian. All right? So the first thing we need to do is, so remember the expression. Let's look at that. Do I have it written here? No, I do not. So we need to do two things here. We first, for the Hamiltonian, we first need to do the Fourier transformation, which brings it from these cell bases to the from the cells which are the lattice vectors back to the k basis. And specifically, I want to bring it in for each k here, right? So first I will do the Fourier transform, and for that I'll have a Fourier transform phase, which is going to be 2 pi I times the dot product of k with the cell map. Except I guess the cell map is n by 3 and my k is just a vector of length 3, so I should put the k on the other side. So this will calculate e to the I k dot r for each r minus r prime rather, each r minus r prime in cell map, right? In the original expressions I just had I k dot r, but here I have 2 pi I. The reason for that is both cell map and k are not in Cartesian coordinates. They are in the fractional coordinates with respect to the lattice basis and the reciprocal lattice basis, which are inverses of each other up to a factor of 2 pi. So that factor of 2 pi comes in here. So when I write this expression in lattice coordinates, that is real space lattice and reciprocal space lattice, I have this extra factor of 2 pi. Okay? Now once I have that phase, so this is just going to be one number for each cell. I can compute my Hamiltonian at a particular k by so I can do it something like this, where I multiply h Swanee by phase and then broadcast that to the same dimensions, because the same phase applies to that entire 5 by 5 matrix, and then I sum this along axis equal to 1. But we'll simplify this code in just a second. Let's leave it here for the time being. Yeah. So this will now give me just a 5 by 5 matrix, which I can then diagonalize. Oops, this should be axis equal to 0, sorry. 0 based index. Okay, so what I'm doing here is I'm computing the Fourier transform phase, summing over the phase multiplied by each entry in Swanee. So this phase is along the first axis, which is where I had h Swanee had n cells by 5 by 5. So and then I sum over that axis. So I'm multiplying each cell of the Hamiltonian by its appropriate phase and adding them up.
So obviously we're going through this, k is changing, but you're like rewriting over UK every single time.
That's right, yeah. So I'm not using UK yet.
Okay.
Yeah. So I can, that was just to show the shape of it, but yeah.
But the UK for one k is not the same.
Is not the same as the other, yes. And we will use that in a subsequent calculation. Yeah. Yeah, that's right. Right now UK is not being used. Okay, but we can simplify this a little bit. We don't need to write it in this form. We can use tensor dot to do this multiplication. So H Swanee is n cells by 5 by 5, and phase just has dimension n cells. So I can just write it this way. I can't use dot because it only supports matrices. And I'll tell it how many axes I'm contracting over. In this case, it's 1. So this basically does a dot product where it contracts over the last, so how many ever axes I specify here of the first tensor, and the first same number of axes of the next tensor. So this was just n cells, and this was n cells by 5 by 5. So I will, or n cells by n bands by n bands. So I will just get after this contraction something that's n bands by n bands. Right? And then right now I'm doing this in a loop, collecting together all the energies and adding them up, which gives me this final matrix, which is 179 by 5. So this is the energies for every band for every k point. Right? Now, I showed this here to demonstrate what this looks like, but actually all of these functions that we are using in Python are very nicely vectorized, and I can do this all over all the k points in a single line. So I don't actually need this loop. So I could instead do this in a single shot like this. So I will now take all the k points in my high symmetry path, and I'm going to calculate the phase for them all together. Okay, so k sim is n points by 3 and cell map is n by n cells by 3. I'm going to write it like this, so that dot product works. So this is going to be something that has dimensions number of k points by number of cells. Right? Then when I do this operation, automatically I have number of k points by number of cells and then number of cells and so on. So my resulting H here is going to have dimensions of number of cells by number of bands, number of k points by number of bands by number of bands. Right? And I can diagonalize all of them together in a single line, and I don't need to put anything together. Oh, sorry, it should be k path, not k sim. Okay, so I computed that in a couple of different ways, but ultimately what we have is the band structure. Right? So this is not what I'd shown you. What I'd shown you before was for gold. This is for aluminum. So you can see an almost parabolic band structure starting from this point, which should be gamma. Oops. So let's actually add the x-axis labels. That's the next step. So we can So we had the index and the labels for the k point. So we can label the plot that way. We can further remove that dead space on either side of it. Right? And finally, just to fix the gamma, we can do a quick Python hack like this.
What is that symbol thing you got? Is that just the parentheses?
Which symbol?
From the index?
This one?
Yeah.
So k index minus 1 accesses the last entry of k index. So I'm basically saying set the end of the x range to be equal to the last value of k index, so it doesn't do that extra padding that it was initially doing. Right? So I can check if the label is gamma, and I can replace that with the nice latex symbol. Otherwise, I'll leave it unchanged. Did I miss a parenthesis somewhere? Yes. Yep. So then I can replace those labels with gamma also. Okay, so gamma is k equal to 0. And you can see these parabolic band structures. So this shows that it's a nearly free electron metal. And only at these points does it start deviating. Close to these high symmetry points does it start deviating from that perfect parabola. And of course you have multiple copies of these parabola intersecting up there. That's how these band structures are formed. So this is a nice example of how these multiple bands are coming in the first place. You basically have parabolas centered at all the different Brillouin, all the different copies of gamma, and they all fold up in the Brillouin zone to get these bands. Okay. So now note that the upper range over here are not quite valid. The band structure is correct up to somewhere around here. Once you go high up here, you are limited by how many bands you actually chose to convert to Warnier functions. So these bands, because I only constructed 5 Warnier functions in this data set, the bands here are not properly represented. So let me, at least for now, indicate that by cutting off the y-axis. Let's say 0.6 Hartleys or so. Okay, so here you can sort of see the bands are complete. There the capping of the bands that you were seeing were sort of the Warnier functions completing the bands that were missing. Okay, so I think it's time for today, so we'll stop here. It's actually 10 minutes over. Sorry about that. So we'll take this from here tomorrow at 3:15. So what we are going to do is we are first going to go from this high symmetry k-point path that just kind of demonstrated what you can get out of this. We will first compute the energies on a Monte Carlo sampling of the Brillouin zone to compute a very simple property, which is the density of states. But even that, when you conventionally calculate it in DFT, you require a very high k-point sampling to calculate. But now with the Warnier basis, with Monte Carlo sampling, you can compute these density of states plots quite easily. So we'll start with that. Then we'll take our first physically measurable property, which is the optical absorption. We'll specifically calculate the imaginary dielectric function due to direct transitions, the first process I mentioned. And I still need to make the rest of the slides, so we'll figure out what's rest tomorrow. Yeah. All right.
Thank you.
Yep, all right. See you tomorrow. Sure, yeah.
So first, when you are near from the M, I wondered, so how do you exactly distinguish in